determine the behavior of individual elements. Maybe you wanted to get the voltage of the resistor R1 or the resistor R2, or maybe the voltage across L2, or maybe the current. Okay. Now, in order to understand the analysis, or in order to understand the behavior of the system, we need to get a certain element or certain parameter that can define everything, no? So that's why okay, so using techniques analysis, no? So the KVL, KCL. So we can solve for this circuit. We can solve this using KVL, no? Summation of voltages. Okay, so we know that summation of voltages is equal to 0. Okay, so I hope you see this point, no? Okay, so this one here on the you have here is the VL. Okay, the voltage across L1, so which is LDI dt, and the current passing through L1 is I1 minus I2. Okay, and you have here the, okay, so you simplify the equation, and then you have here the constant, because we're still in DC, no? Okay, so for the I2, loop I2, conduct KVL, and then you will have the same equation. This one is uh, the voltage across L1, voltage across R2, and then voltage across L2. Okay, so you just arrange that one and you get this equation. Now, as I said, choose one one of the equation, or sorry, one parameter that you can then understand the whole system. Okay, so here it's better to use I1. Okay, you can also choose I2. Okay, but here sufficient, you can get I1, and then if you can get I1, the behavior of I1, okay, the response of I1, then you can get I2, you can get BR1, BL1. Okay, so everything, no? So our goal is to get I1, okay, using the two simultaneous equations. Okay, so simultaneous equations, what is that, no? So these are equations, okay, of your system that defines your system, because this system here is one system. I mean, the elements are one circuit. Okay, sorry, one system. Okay, defined by that system of equations. Okay, so we can call it system of ordinary differential equations, because in the first order, no, differential equation. Now, so therefore we can get I1 and then remove I2. As I said, no, we try to look at the behavior of I1. So now the first and the second equations are not sufficient, so we try to derive the first equation. Okay, I think you know how to derive the whole equation, and then use that use this one, the equation, together with the first and the second, this one and this one. Then you can get this expression. Okay, so I will not go into detail, but you can do this, no, removing I2. So to remove I2, you need these three equations. Okay, and then now you are remained with I1, okay, as your equation, I1. Okay, so if you what can you observe from the equation? So you have, okay, to the second d squared I. Okay, and you have constants here, and if you can observe, you can actually get this one. Okay, if you can recall the how to get the solution. Okay, we assume actually here that the I, okay, I is equal to a e to the s1t plus b e to the s2t. Okay, so if you can recall, okay, so we assume that one as our solution, and you will get s, okay, as the e to the st. Okay, so this one, the root, we call it the root of the equation. Okay, the ordinary differential equation. I hope you were able to understand it in your ODE subject. Okay, and then so the transient solution depends on the roots s1 and s2. If you can recall the, okay, the graph, no, okay, for the charging of the inductor. So in this case, inductor lang, no. So you understand the transient, no. So from certain number to a certain number. So from 0 to 5 uh, amps. Okay, so that's your behavior, no, of your inductor or the current. Okay, so that's a transient. Okay, temporary, or yeah. Uh, so it depends on the roots S1 and S2. So the time constant, okay, RL, L over R, okay, in that sense. Okay, and then also with the initial conditions, whether the inductors are um, charged or uncharged. Here we say that the initial current is zero, meaning the current across L1 is zero at time is equal to zero. And then you have here the first derivative of I. Okay, the changes of I is equal to V over L1. So actually you can get this one from the equation here. So given that time is equal to zero, this becomes zero, this becomes zero, because di over dt is equal to uh, actually d1. Okay, so you will cancel that one, and then this one is zero also, and then so this one will cancel this L2, so you will get then L1, cancel L1, and then so what remains is R1, cross multiply it, so um, then okay, so later you will see later, no, actually this one is can be a given. Actually, I think I made a mistake. Actually, I think this one here is the zero, but it's quite. This one is usually given. Okay, so the changes of your current, no. So di over dt from t is equal to zero. This one, you can derive this one from these equations. Okay. Um, yeah, but we'll not go into that detail, no. So okay, so that's in the ODE. And then lastly, that the infinity value of your current is equal to V over R1. This one is physical. We can observe this physically, so that at time is equal to infinity, this one is fully charged. Your inductor is fully charged. So therefore, the current, let's say I1, this should be I1. Okay, so I1, the current I1, you have a voltage source, and then you have the resistor here. Okay, and so if the inductor is fully charged, it becomes shorted. Okay, so meaning there's no inductance anymore. Okay, I mean the storage is already full. Okay, so therefore your I is equal to V over R1. Okay, so because the inductor is in 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 capacitor, the voltage, the capacitor becomes open. Okay, if time is equal to infinity. Okay, so then um, having you can express I1 here given the initial conditions, and then you can get already I2, VR1, VR2, VL1, VL2. Okay, and then you can understand the behavior of the circuit. Okay, so that's the idea, and that defines the circuit and also the steady state analysis. Now, why is it steady state analysis? Because you will see the transient, no? Okay, the behavior. So you may not be able to graph the steady state, but you already performed the simple RL circuit. You see that there's a steady state, no? Because the value here is DC, okay, a constant value. So therefore, you will see the transient, no, or steady state. Okay. Now this one is in time domain analysis. Okay. How much more if you are going to you have a complicated circuit. So first here you notice already that it's very complicated, no? And imagine the circuit that we have now. We cannot do this, no? We cannot simply do this kind of thing, no? So this is the classical way of doing, classical way of solving and analyzing a circuit and other systems, dynamic systems, which we will discuss in the next the last lesson. Okay,